Hello everyone. So in this video we will go through accuracy, precision, recall, F1 score, confusion matrix, ROC receiver operating curve, receiver operating characteristic curve, and receiver operating characteristic curve, and area under curve AUC. And we will see what are these terms and we will try to understand them. So first is let's get some definition first. One is true positive. So true positive is what you predicted to be true is actually true. So just remember, both sides is positive is the case and it became true. So you predicted something to be true and in reality it also came to be true. And true negative, what you predicted to be false is actually false. So what you predicted that it will not come true, it has actually not come true in reality. It's been false. So these two are easy, like true positive and true negative. Now false positive. So what you predicted to be true is actually false. You predicted that something will happen, but in reality, after some time we have realized, or based on the data we have realized, that it's not. It was false or it is false. And last one is false negative. So what you predicted to be false is actually true. So it's the reverse. So in this case, false positive, you predicted something to be true and it came out to be false. And in false negative, you predicted something to be false, but in reality it came out to be true. So we'll see it with some examples. So let's see detect cancer. So positive case, you have to predict whether cancer is present. And negative case will be cancer is not present. So in this case, true positive will be that you predicted cancer is present and in reality also it is present. So it's a good case. You predicted that a patient who came for test and the test said present, and in reality, so probably he do some further test or something, in reality also it came out to be true. Next is true negative. You predicted cancer is not present and in reality also it is not present. So it is not present. So both the cases, like what you predicted or what you not predicted, came out to be true. So from a scientific point of view, so both are these are like good cases, we can say. Means we haven't made mistake in first two situations. Next is false positive. So predicted cancer is present, but in reality it is not present. So you predicted that cancer is present, but in reality it is not present. This we came out because we have the knowledge of the data point, or after we do some more additional test, we can say. And next is false negative. So you predicted cancer is not present, but in reality it is present. So it's other way around. So you predicted something is not present, but later on in reality, or based on the knowledge of the data point, we know it is present. So in this case, you don't want to have false negative. You don't want to have false negative in this case, as most people would not bother to do further test. So if you say somebody, like if you falsely, if you predicted that somebody cancer is not present, they will not bother. So that are present may arise after 5 years, 10 years, or few years later that he had cancer, and when he came for the test first time, let's say I'm a clinic who test for these cases, and I say no, you don't have, but he realized after few years or 10 years, 5 years that no, my first test which I done 5 years back wasn't right. So it's a very serious case, right? So you don't want to have false negative case in this kind of situation. So it depends on the domain also, like which domain we are investigating upon. So let's say it is okay to have false positive. So this case, false positive, that predicted cancer is present, but in reality it is not present. So it's okay because let's say a healthy person, by mistake you say they have cancer present. So they can actually do one more test or some deeper level test to make sure that it's not there, right? So they will be safer. So safety is more important, right? So in this case, as the false alarm can be negated by an extra test. So this is false positive. You can see, you can remember as false alarm. So let's say for safety, sometimes false alarm go in office buildings, right? So we always say like it's okay to have false positive because life, safety of your life is more important. So it's okay to have some false alarm, because you can actually go out and figure out, okay, this was a false alarm, but your life is more important. So same in this case, anything medical, same situation. So you can have, you don't want to have false negative because people would not bother. But in this case, if it's false positive, they can do some extra test to confirm, okay, no, the first test was wrong. So you don't want to have this kind of situation. So we'll see one case about detecting spam. So positive case, spam email. Negative case, not a spam email. So true positive would be predicted email is spam, and in reality also it is spam. So what you predicted also came out to be true. True negative, predicted email is not spam, and in reality also it is not spam. So both are not. Now false positive. So predicted, so positive, you just see what we are trying to predict. So this just we have to read something like this, what we are trying to predict. So just put that in first statement, first 2, 3, 4 words, like predicted email is spam, but in reality it is not spam. So this is false positive. So you predicted that something is spam, email is spam, but it came out to be false. So it is not spam. And false negative, predicted email is not spam. So negative first part will come here when you read, not the false part. False part will go later if you want to like read it. So negative case is not a spam email. So predicted email is not spam, but in reality it is spam. So it is false negative. Now you don't want to have false negative in this case, as most people would miss the email completely if it goes into the spam folder. So we don't want to have false negative that you predicted email is not spam, but in reality it is spam. So because if you don't want to have false positive, this one, because if you predicted email is spam because you have done some algorithm or write some automation, as soon as, for example, in Gmail, if it is straight away goes to the spam, genuine email, like, and then you will not have any chance to read it, right? So you don't want to have false positive in this case, because you will completely miss that altogether. But it is okay to have false negative. So we can have this one, predicted email is not spam, but in reality. So because in this case, as spam email when seen by the user, because it will go to the inbox by the user in inbox folder, can be manually marked as spam. So it's okay. So that's why in Gmail you would see that you will see some spam email in your inbox. You will most of the time click spam, right? So Gmail is also doing the same. They are okay to have some false negative, but it would happen very less that some email sent by your spam, some friend or something goes into spam directly, because that happens less, and this happens more if you would have observed, right? Okay. So this and cancer, if you see, they both are exact opposite. Depending on the domain, we have to go with what is worse. Like, what is it okay to have false positive, or is it okay to have false negative? So depending on the domain, we have to ask this question, and we will see what is the importance of this. So next is confusion matrix. So confusion matrix looks something like this. So you have like predicted condition, what you are trying to predict. So predicting, so the first is predict positive, whether you have predicted something to be positive, and this side is you have predicted something to be negative. So this is a matrix, and this side you have actual condition. So you are trying actual positive and predicted positive, means this is a good case. And same way actual negative and predicted negative. So this column, this is a true negative, means what you are predicting is also not true. So it came out to be false. So this and this is good case. So here in this diagram, for example, this lady is pregnant, and this doctor is saying after some test you are pregnant, and which we can also in reality we can also observe that, okay, true positive, means the test done by this doctor was correct. and it is true positive, and we go to this column. So doctor is saying you are not pregnant, and from the photo like this we can say okay, this is also true negative. So this lady is not pregnant, so okay, you are not pregnant, and this is also true. Now actual positive. So actual, we can say the woman is pregnant, but doctor is saying you are not pregnant. So this is negative, like negative but false. You are like what you predicted and actual is not true. So this is false negative, and this is also known as type 2 error. And this case is false positive. So we are saying positive. So this doctor is making statement you are pregnant to a man. Let's say this is a robot or a machine. Okay. So this is the robot or the machine has said like you are pregnant, but we know from the fact that this is information is false because the robot or the algorithm or machine has made a mistake. So we know it's a false positive. So it is known as type 1 error, or it can be also called as false alarm from the office security analogy that I gave before. Okay. So confusion matrix. So predicted condition PP, positive predicted or predicted positive, predicted negative PN, and then you have actual condition positive, negative, and then you have true positive, false, true positive, true negative, and this side you have false negative and false positive. And we will just put some like arbitrary numbers. So true positive is 40, 30, 20 and 10 because we will do some calculation. So just remember this number 40, 20, 10 and 30, but anyway I will include that also. So first measure is accuracy. So accuracy is calculated as something like this. You have true positive, true negative. So just remember the diagonal, the first and the last diagonal, right? So true positive was the first and the last. So we are just looking at the diagonal. So we are looking at the good cases divided by the total population. So whatever based on the number. So you have 40 plus 30, 40 plus 30 and the other. So this total was 100 total population. So in this case, the accuracy for our confusion matrix is 70% and 0.7. Okay, so this is one of the matrix, but we have some other matrix as well. For example, precision. Precision is true positive divided by true positive plus false positive. So precision is more just think of it as like how precise you are with your positive observation. So like what you are trying to, for example, you are trying to detect cancer, right? So what is the percentage? What is the precision level? So how much you have true positive and false positive ratio? So I'll just put those numbers like 40 by 50, and it would be 80%. So you will see like accuracy is a very rough measure because you see, for example, in the cancer detection, accuracy was 70%. Now the precision has gone 10% more. So because we have to be more precise with our observation or the matrix, so that's why we are like we are coming up with new matrix because accuracy is not good for something like imbalanced data or where we have too many observation and it's all spread out, and we want to detect a certain specific condition. So that's why we have this other matrix because as a layman you will always think that you just go ahead with accuracy, right? But when we deal with machine learning and all, we have to come up with newer matrix. And same is recall. Recall is true positive divided by true positive plus false negative. So in our case, we have 40 and 40 plus 20, it's 67%. So recall in this case is 0.67. So this is just for you to know. Recall is also known as true positive rate, and this will come later on in some slides which will leverage this concept of true positive rate. For the time being, just remember that recall is also known as true positive rate. Recall is also known as sensitivity. Now false positive rate, which is false positive divided by false positive plus true negatives. So based on our example, it is coming out to be 25% or 0.25. So basically false positive rate should be less because it's false, right? False positive rate means you are making mistakes. This is not a good situation. So you want to be as low as possible. So that's why this number is coming to be less. Okay. So there's one more matrix which is the right sweet spot between precision and sensitivity, or precision and recall. So which is called F1 score. So it's a harmonic mean of precision and sensitivity. So this word is sensitivity is same as recall. So just have to change that. So precision plus recall, this is actual formula. So in this case, if I put all the numbers, it would come to 0.73 because it's a right balance. So you will see, you remember precision was 0.8 and recall was 0.67. And if I have to balance these two together, it would come something in between. So that's why it's coming to 0.73, and precision was 0.8 and recall was something like 0.67, right? And it's a balanced or we can say happy medium. So now we'll just go through some scenarios where high recall is more important. So this is also a formula. So, and I'll explain why this is important. So for example, you need high recall in cancer or any serious medical condition detection, flagging fraudulent transactions, not safe for work images detection. Okay, so why? Because it is okay to have some false positives, which we have seen in cancer example. So it is okay to have false positive in fraud transactions, because this can be later on claimed by some extra calling customer can call or something. Because if fraud transaction has already happened, both the bank can lose money or the customer can lose money. So it's okay to like mark, like when the transaction is happened, just say this is fraud, and this can be contested later on by the customer. He would be slightly unhappy or something if it's a genuine customer, but at least he would be made safe from somebody trying to steal his money, which can be rectified later by. So it's good for both bank as well as the customer. But it is unacceptable to have false negative. So we should try to have avoid false negative in this case, because if, for example, fraud has happened, so somebody has lost money, right? Depending on if it goes to the court, what is the decision, right? Somebody would lose money. So next is high precision. So this was the formula, and we'll see wherein high precision is required. For example, recommendation system and YouTube recommendations. So recommending a lot of irrelevant products, so like false positives. So customer wouldn't be happy because if there are too many, because the end user experience would be bad. Same email spam detection. For example, in this case, I have worded it differently. No genuine email should be classified as spam. So false positive. Same, I think it will become more clear, like death punishment to a criminal or punishing an innocent person. For example, let's say somebody is there is a court case, and some innocent person is declared as positive, means punishment, punished. So positive in this case, person is punished. Just read it like that. But it came out to be false. In reality, it is false. But for that person, it's earth shattering, because some innocent person has been criminalized and he has to serve a sentence. So that's why in this kind of situation we have to have high precision. It's okay to have some criminal person let go, but it's more important not innocent person to be punished. So approving bank loan to a good customer. So approving a loan to a bad customer is disastrous. So in this case you have to read approving a loan. So approving a loan is a positive case, and it shouldn't be to a bad customer it shouldn't be like false. So in this case, false positive must be avoided at all cost. So because this one is right, if you approve a loan to a bad customer, which will be like false positive, so bank will lose money in this case. So in this case, false negative is okay, because if there is a genuine person who is not given a loan, it's okay for the bank point of view, right? because at least bank will not, bank would like to avoid false positive and same death punishment to or some kind of punishment to a regular person, and genuine email should not be classified spam or irrelevant products, like you are recommending video, for example, positive, so this is the case, and it is irrelevant, so it's false, so there is a bad customer experience, and false negatives are okay in all these 4 cases. Okay, now we'll come to ROC curve. It's called receiver operating characteristic curve. Is a graph showing the performance of a classification model at all classification thresholds. So we are going deeper into like actual real world application or implementation. So that's why this is new term ROC curve. This curve plots 2 parameters: true positive rate, which we have seen, and false positive rate. And this is the formula, true positive rate, which we have already seen, true positive divided by true positive plus false negative, and same false positive rate. So false FP will come up, and FP plus true negative, and this one TP plus FN. So ROC curve looks something like this. So I'll just try to explain. So x-axis we have false positive rate here. So we have false positive rate on the x-axis, and the value starts from 0 and goes all the way to 1. And y-axis we have true positive rate. Value starts from 0 and goes all the way to 1. And at this point, FPR plus TPR is 1, 1. So X comes first and Y comes next. So when we start, we will start something like this, a line, a graph. So this is the graph. It starts from A, B, C, D, E, F, G, H, I, J, K, L, K, M. So these are the points. These are the thresholds. So we start with first threshold, which is A, and it always starts with 0. So at 0 threshold, you have both true positive rate 1 and false positive rate also 1. So that's why it's 1, 1. So you have another threshold. So this threshold can ranges between 0 to 1. So just think like 0 to 100%. So let's say this one is 0, and then 0 to 1. So this one, for example, 5% or 0.05, and I calculate the same. So at this point, I calculate what is the TPR and what is the false positive rate, and I put a dot. Same at this threshold. So this could be like, for example, 10%, 0.1. I'm just giving it for the sake of for the argument. So this at this point, there will be some value of FPR plus TPR, and for example, at this value D, it could be, let's say, 20% or 0.2. So at this point, 0.7. So we can say 0.7, something like this here, somewhere over here. Your FPR is 0.7 and your TPR is so if you just come here, 0.9. Same, I'll just go with 20%, 25, 30. So you can have different, like 20, 30, or you can have 25, 30, 50. And at this point, my FPR is coinciding with 0.4 and 0.8, and then same 0.2, 0.7 and 0.1, 0.4 at different thresholds. So this could be like, as I mentioned, 25, 30, 35, 40, 45, 50, 60. You can have different thresholds. And so this is so at all these A, B, C, D, we are plotting at this confusion matrix. So we have one, let's say we have one confusion matrix for one model. Now at different thresholds, like we can have 20 different thresholds, as I mentioned, 5, 10, 15. We'll have 20 different confusion matrix, and we will just plot these points. And these points, all these points will be like ROC, receiver operating curve, characteristic curve. And our goal is to be as close as this point here. So if our graph, so this point, right, H1, we can say H is the closest to this point, 0.2 and 0.7. So in this case, our true positive rate is 0.7, which is high. So our true positive rate, which is a good thing, is high, and our false positive rate is 0.2. So this is near, or this. So these two are very close to this point. So we have to decide whether. So these two points are ideal point for in this case. So this one is false positive rate is 0.4. It has gone 0.2 to 0.4. So which is like it has become worse, but from 0.7 to 0.8 it has improved the true positive rate because we have gone up. So 0.7 to 0.8 it has gone up, which is good, but 0.2 to 0.4 it has gone up, which is bad because it's false positive rate. And so an ROC curve plots true positive rate versus false positive rate at different classification thresholds. These are the classification thresholds. I will discuss more. I'll explain thresholds in next few slides. So lowering the classification threshold classifies more items as positive, thus increasing both false positives and true positives. So lowering means you can threshold, for example, 0. So in this case it is the lowest. So at lowest point, all points will be regarded as positive, regardless whether they are true positive or false positive. Everything will be said is made as positive. But as we increase the threshold, this number will go down. So to compute the points in an ROC curve, we would evaluate a logistic regression model many times with different classification thresholds. So this I will show you. And you will want to have high TPR. So you want this value to be high, this y-axis, because it's a true positive rate. So if it is 1, it is perfect. And so if it is 1, it will come something like this. It will just move from 1 from 0 threshold. It will come here and here. And you will want to have low false positive rate. So false positive rate is this. So you want to go as much as near to 0. So you want to be 0 or 0.1 or 0.05, as close to this, can say something like this area. So now, since after we have plotted this ROC curve, now what we can do is we can just join this and we can see what is the total area here. So this is called as ROC curve, area under ROC curve, this whole thing. And this one AUC measures the entire two-dimensional area underneath the entire ROC curve from, so this from 00 to 00111. So this will have maximum value of 1 because our graph is going from 0 to 1, and these are 0.2, 0.4. So if this whole thing maximum value, if a ROC curve goes full, then it will be a maximum value of 1. In this case, it will be somewhere between 0.7, 0.8, and if it is here like half line will be 0.5. This half triangle, right angle triangle, this will have 0.5 value, and this one is 0.5, and this is somewhere in between, so it will be 0.7, 0.8. And AUC provides an aggregate measure of performance across all possible classification thresholds. So we have all these classification thresholds like 5%, 10, 15, 20, 25, 30, 35, 40, 50, 60. So we have made this and we have plotted this and we have come up with this particular graph area. And one way of interpreting AUC is the probability that the model ranks a random positive example more highly than a random negative example. So we'll see that. And if AUC is equal to 1, best model. So of course AUC best model, like it will be close to 1, but this is just for theoretically. So if it is 1 means the whole thing. So it will come to this point somewhere over here. The true positive rate will be 1 and false positive rate will be 0 somewhere over here. And if it's 0, if it is 0.5, it will be useless model. So if it is, if your thresholds look something like this on this line, right? If it on this line, it will have a 0.5 and it is useless because 0.5 basically means you are flipping a coin and depending on, you are just saying heads or tails like one by one randomly. So let's say cancer detection, one time you say yes, for next patient you say no, yes, no, yes, no, yes, no. So of course you will get 50% of the time, so it is pretty much useless. And an area under curve helps in in determining which model is better. So we have two models, left hand side and right hand side. So our goal is to have, so let's say two data scientists or machine learning engineer have plotted this graph, and left hand side this ROC area under curve comes to 0.7, and this one you see slightly area is more, so let's say it's 0.8. So we can tell the machine learning engineer second model is better, or if it is like two model we are comparing, so let's say one we have logistic regression and random forest, and right hand side is random forest, so we know this one is better because there's more area under curve. Okay, now I'll just try to explain the cutoff thing, threshold cutoff for the ROC. So default threshold, for example, is 0.5. So this is the line, and this line can move up or down. So it can be at 0, it can be at 1, or it can be somewhere between. So if it is 0.5, so all the data points which is above this line, this threshold cutoff line, everything above the threshold will be predicted as positives, and everything below the threshold will be predicted as negatives. So let's say default is 0.5. So these data points which is correctly identified, so green, so they are coming in green zone, so they are positive, this positive we have correctly identified. But these two in real were negative, but they were predicted as positive. So these are false positives. So we have our model has made two mistakes here. So there are two false positives. So we have made two mistakes at this side. Same way, below this, everything should be red. Everything should be negative. So this is negative, actual also negative, and all these points are negative. So we have not made any mistake with these 8 data points, but these two, these were predicted as negative. Predicted as positive, but they were negative. So these are false negatives. So these two data points we have our model has predicted wrong, because it was predicted as negative, but in real it was false. So that's why these two were wrongly predicted. So we have, but still our model is okay, because we will always have some kind of a cutoff. So this is the default. Okay, now if I make the threshold go down, like this is now the threshold or the cutoff is 0.1, and if I make this 0.1, all these red points, they will become false positives. All this will become false positives, because these were predicted positive, but in reality they were not true. So these 1, 2, 3, 4. So, but in some cases, depending on the domain, as I mentioned, for example, cancer detection, we would like to have a very low threshold or the cutoff. Instead of going with 0.5, we will say better to have 0.1. And it depends on the domain, like which domain we are working with. So so as I mentioned, it's okay to have false positive, because a person can do an extra test to make sure that that's not true. So that's why we will have bring down the threshold. Same, if I make the threshold go up like 0.9, all the green points will become false negatives, but above everything will be correctly identified, but here these points will become false negatives. But this is okay in some different domain, like as I mentioned, for the email spam detection, because it's okay to have false and negatives, because user can still can see the spam email in the inbox and manually can mark as spam. So now just coming to the last thing. So the threshold can be seen with some of the places. You will see some graph like this. So it starts, for example, cancer detection. So you have starts with like threshold is, it goes from 0 all the way to 1. So these are my points. So let's say 5%, 10, 15, 20, 25, something like this. It goes 50, 60, 70%. And then finally, these are the points 0 to 1. This is the last. And herein I plot on the graph. So here I will have this area, right? This is true, negative. And then you will have a cutoff. So if you go back, you will see that this point H is coming to 0.2, 0.7, where I feel is the ideal cutoff point to have the right mixture of the best performance of the model. So, and this is true, negative, which is a good case, and right hand side will be true, positive. This whole area, this part, true, positive, and this part is true, negative. So this is okay. This part we have correctly identified. Now the model has messed up at this part. So this cutoff, anything left to the cutoff will be negative, will be predicted as negative, and anything right will be predicted as positive, regardless whether what is the actual. So all this will become false negative because they were predicted as negative, but it's false because they were in real positive, and this part will be false positive because these were predicted as positive, but in reality they were false. So this were the messed up part. So that's why what we have seen in the previous, the threshold. So we can move the threshold, for example here. If we move it here, we will identify all the positives, but we will have false negatives more, and we can move it over here. So this is like, you will see in some places like a graph like this also. And just to like illustrate, so when you have very clear separation, so you have true, negative, and you have a cutoff, and then you have a true, positive. So this model has a very clear separation between true, negative, and true, positive. There is absolutely no overlap. So this will have some area under curve very close to 1.99 something or something like that, because there is a very clear separation between true negatives and the true positives. Now if the graph looks something like this, you have true, negative, and then you have true, positive, and there is a cutoff line, and herein there are few data points which the model has messed up, like false positive and false negatives. So that's why they are in different area bracket. So these were incorrectly identified, but still this is okay. This is like generally like, so in this case the area under curve will look something of this like 0.8, somewhere around this range, and this is a very decent of fair or average model. So you will have true, negative, true, positive, but there is a very huge overlap, and there is a huge data points which were incorrectly identified with false positive and false negative, and this will have AUC of something like 0.7, around somewhere in that range. And this is the useless model which I talked about. You have true, negative, and true, positive, both are overlapping because basically the model is saying yes, no, yes, no, yes, no, yes, no all the time, or just saying yes all the time or no all the time. So this is pretty much like flipping a coin, and that's why the area under curve will be like 0.5, because it's just like a random classifier. So with that, thanks for watching. Bye.